Welcome to this session. Here we shall discuss about the selection of a castable for different areas of the blast furnaces or other furnaces for repair jobs or a new installation of a lining and different types of castable. Why 90% high alumina castable is not suitable for the repair of throat area of blast furnaces? How to select a castable? Here the discussion is about the use of alumina silicate castable. Alumina in the pure form has the melting point 2072 degree centigrade and silica in pure form has the melting point 1710 degree centigrade. In the alumina silica system, when alumina is mixed with the other oxide silica, the melting point of the mixture decreases. When alumina content of the mixture decreases from 100% to 69 to 77%, the mixture melting point decreases to 1890 degree centigrade for mullite composition. For other composition, melting point comes down to 1587 degree centigrade. In the range below 72% alumina, mainly mullite and cristobalite crystals are formed in the mix. Now, when the Al2O3 is in higher side, more mullite crystals will be formed and that is desirable to provide high temperature strength. Some terms are often heard in dealing with these types of castables: low alumina castable, high alumina castable. Generally, castables which contain less than 45% alumina is termed as low alumina castable, and containing 45% or more Al2O3 is termed as high alumina castable. Other familiar terms are 40% alumina castable, 60% high alumina castables, which means castables containing minimum 40% alumina and minimum 60% alumina in the mix respectively. Let us suppose a 60% high alumina castable. This means that this contains minimum 60% Al2O3 in the composition. So, rest 40% is mainly silica with other modifier ingredients like silicon carbide, zirconium oxide, alumina spinel, etc., along with other impurities like iron oxide, calcium oxide, magnesium oxide, sodium oxide, potassium oxide, etc., known as fluxing agents which form low melting compounds. So, this is a complex system. So, with the increase of service temperature, percent alumina content in the mix should be more. That means we require 70% or 80% or 90% alumina content in the castables along with fluxing agents as minimum as possible according to situational requirement. Thus, it helps to select a castable for a particular use. Another case is the use of a high alumina castable, say 90% high alumina castable, service temperature 1700 degree centigrade at a low temperature zone, say 400 degree centigrade at the top of a blast furnace for repair. Our common belief that will be very much suitable as it can withstand very high temperature. The expression of this castable also shows very high value of hot strength like high refractoriness, high RUL, high temperature bending strength or high hot MOR, indicating high load bearing capacity, providing high temperature structural strength. But that is not a suitable selection. Why? First, cost is very high because of high cost ingredient used in manufacturing. To understand that, we have to know the strength development in castable after application. Castables are generally containing high alumina cement as binder, and in some product where cement is not desirable, hydratable alumina known as raw alumina or silica sol or alumina sol are used as binder. When water is added during preparation, these binders get hydrated, forming compounds which are able to bind other ingredients of the castable to provide hardness to the product. During heating up to a temperature of 200 degrees centigrade, the physical water like moisture evaporates, and when temperature is further raised to 550 degrees centigrade, the chemical water known as water of crystallization comes out, breaking the hydraulic bonds. In this situation, the cast products becomes weak. With further increase of temperature, the ceramic bond or refractory bond start forming from 800 degree centigrade. With further increase of temperature to 900 degree centigrade, the dehydrated compounds again crystallizes. What is this refractory or ceramic bond? Actually, at higher temperature, the very fine particles present in the mix start sintering and form low melting viscous silicate compounds in the matrix around the aggregate particles and bind them, keeping the overall structure strong. What is called matrix, which come to our mind? All finer particles less than 100 millimicron form the matrix. In the castables, there are bigger size particles, say 6 millimeter to 100 millimicron. These are known as aggregate particles which help to take the load in the cast structure. High alumina cement or hydratable alumina or silica sol or alumina sol as binder like Portland cement in binding the building bricks. Different finer particles, generally 1 to 10 millimicron, like silica fumes less than 45 millimicron size, alumina fines less than 6 to 8 millimicron as fillers like sand in our building construction. These microfines have very high surface area and undergo sintering, forming very viscous liquid in the matrix around the aggregates, and that bind the aggregate particles. Ultrafine additives of sizes 1 millimicron or less are there in the castable like sodium citrate, sodium hexametaphosphate, lithium carbonate, etc. to control the setting of the castable. If it is very quick setting, then that will not be workable. If it is very slow setting, then industrial condition will not allow that. So these additives help to control the flow behavior and setting of the castable. These cement binders, microfine fillers and additives fill the voids and form the matrix in between the aggregates. Now castables with high service temperature must contain higher percentage of alumina and low content of fluxing material as minimum as possible. So at low service temperature like 400 degrees centigrade, when 90% high alumina castable is used, viscous liquid formation in the matrix will not be there to bind the aggregate and to develop a strength after breaking of the hydraulic bond. That means the abrasion resistance, CCS, load bearing capacity will be insufficient as the aggregates are loosely bonded. So that cannot be suitable for that low temperature zone. Moreover, it will be a costly affair. Similarly, a castable with low service temperature, if used at a high temperature zone, viscosity of the liquid formed in the matrix will be very less and it will be insufficient to bind the aggregates to develop a strength in the cast product. For low temperature used, the aggregate particles generally consist of low alumina content, low melting and lower cost aggregates as raw materials, which will be easily fused if used at high temperature zone, leading to failure. So we have to use the castables considering its service temperature. To understand the use of different castable with improved high temperature strength for different purposes, we have to understand the castables in other ways of classification. Another term is always heard of about the castable. Sometimes expert says conventional castable, which contain calcium oxide more than 2.5%, or low cement castable known as LCC, which contain calcium oxide less than 2.5 up to 1%. Another class is the self-flow castable, which contain calcium oxide less than 2.5% and up to 1%. And the other class is the ultra low cement castable or ULCC, which contain calcium oxide less than 1% up to 0.2%. And the other class is ZCC or zero cement castable, which contain calcium oxide less than 0.2%. This calcium oxide mainly comes from the high alumina cement used as binder. This clearly indicates that conventional castable contains very high amount of cement, generally 15 to 40% high alumina cement in the composition. We have to understand about this classification and where to use these castables. Conventional castables require as much as 8 to 20% water for its preparation Because of the requirement of high amount of water, more pores will be developed during drying or heating. This high amount of water during preheating as vapor creates excessive pressure inside the cast product and come out creating pores. As this requires more water for its preparation, so more pores will be formed in the cast product. So CCS, RUL and other high temperature strength will be less. Permeability will be more, so less resistant to corrosion. So this is not obviously suitable as abrasion and corrosion resistant product. Furnace throat has to withstand very high abrasion from the charging burden. Because of higher CO content coming from the cement, some low melting compounds like gelignite C2AS melting point 1593 degree centigrade and anorthite CAS2 melting point 1553 degree centigrade are formed at a temperature of 1200 degree centigrade. So at high temperature mechanical strength will be less. So it is not suitable for high temperature use. To get rid of the harmful effect of higher amount of CaO coming from the use of higher amount of high alumina cement in the conventional castable, another class with low amount of cement has been developed. This is known as low cement castable or LCC, containing 4 to 8% of high alumina cement. Because of the lower amount of CaO from the high alumina cement, formation of low melting compounds will be less and this can be safely used at higher temperature. Moreover, because of the lower amount of calcium oxide in the low cement castable, lower amount of will be required for hydration or setting reaction. Microfines like fumed silica, alumina fines are used that replace part of the cement and fill the voids in between aggregate. But these microfines require no water for hydration. So overall requirements for water during mixing the castable will be less. After drying or preheating, porosity of the product will be less, forming a very compact product. So high temperature mechanical strength, abrasion resistance, corrosion resistance and refractoriness etc. will be more and that will be suitable for high temperature use. This type of castable develops a thixotropic property when mixed with less amount of water in a mixture. The property of this type of castable is very much sensitive to water addition. An example shows this effect with certain low cement castable. When mixed with 4 to 5% water, CCS developed was 110 megapascal, but mixing with water 6%, CCS reduced to 80 megapascal and mixing with 7% of water, CCS was further reduced to 70 megapascal. So to get an easy flow mix, water addition should not be more than the specified norm. For proper flow of castable, mechanical vibration is required after placement of the castable in position. This type of castable gives a very viscous mass during preparation with a specified amount of water, for which pouring in a narrow space is very difficult, and use of a vibrator properly is also very difficult, as in the case of casting blowpipes in the blast furnace and skid pipes in the reheating furnace. So, another class of castable having same CO content has been developed in 1990 as self-flow castable. Only the particle sizes in the mix are designed in such a way that with low amount of water, say 4 to 5% during mixing, the mix can flow under gravity with its own weight, and no vibration is required after pouring the castable in position. Next category is the ultra low cement castable or ULCC, containing 1 to 2% of high alumina cement. Because of the detrimental effect of calcium oxide coming from the cement used as binder, use of high alumina cement is reduced more in ULCC or ultra low cement castable for casting a special type of product like slide gate plate, nozzles for ladle, etc. If we want very improved high temperature strength and try to avoid cement as binder to get rid of the formation of low melting compounds by calcium oxide, there is another class of castable known as ZCC or zero cement castable. In this type of castable, hydratable alumina or silica salt or alumina salt are used as binder. For quick repair or short duration repair, conventional castable is suitable, as it can be applied without anchor, without former. It can be applied on damaged surfaces for developing required thickness by applying with towel, making a towelable consistency for running the furnace for a very short period. It is very easy to install, and drying or heating process is not very much sensitive to the heating rate, unlike that of LCC or ULCC, which lead to the explosive spalling with a high heating rate. LCC cannot be used without former for patchwork with trowel, as it does not stick to the old surface and simply rolls down over the surface. Low cement castable develops very high physical strength, low porosity, high abrasion and corrosion resistance in the cast product after application, but it is very much sensitive to the installation process. Mixture, vibrator, short kitting arrangement is required for its application. So, for a very short duration repair for 24 to 36 hours, it is difficult to apply low cement castable. In all the steps, all the technical norms have to be followed, otherwise that will give rise to a very inferior product. Even the result may be much inferior to that of the conventional castable. The repaired area with conventional castable cannot give a quality product because of its low physical strength. Next plan for repair has to be made accordingly. When time is allowed for proper installation, proper heating up, then at least depending on the temperature of the repairing zone, say more than 1000 degrees centigrade, either 70% or 80% low cement castable can be easily applied. If it is near the tap hole area or in the wash area 80 to 90% castable should be applied. As we opt for high alumina content castable, that means some technical alumina has to be added, either brown fused alumina, white tabular alumina, white calcined alumina or corundum, etc. in the castable composition. These fused grains have very low porosity, high refractoriness, high abrasion and corrosion resistance because of the presence of very low amount of fluxing agents. Hope this discussion will help to understand the repair of blast furnaces and other furnaces with the use of different types of aluminosilicate castables and their classifications. Thank you.